that we're recording. All right. Hi, all. Welcome to the Physics Colloquium. It's my great pleasure to introduce today's speaker. We know him very well, Dr. Nathan Inan. Dr. Inan is currently at Clovis Community College, where he was just telling us how much he loves the job. It's his dream job. Just a brief overview of his academic trajectory. Nathan got his undergraduate degree at CSU Long Beach, came here and did his master's degree with us, I think, with Dr. Ringwald, and then moved on to UC Merced, where he got his PhD under Dr. Ray Chow, where he worked on various aspects of gravitational physics, and actually has continued his work after that, and is currently very active. And a year or two ago, his essay to the GRF contest was given an honorable mention, which is actually a great thing. So anyway, without further ado, welcome Dr. Nathan Inan, and he's going to tell us about Maxwellian mirages and general relativity. Nathan, take it away.
Thank you, Doug. I really appreciate the kind introduction, and I am very excited about this talk. This Lance, who partnered with me in this work, states it very well, that this is an itch that we've wanted to scratch for some time. He's had that, and I myself as well. So this is kind of our opportunity to do that, and I'm very grateful to everyone who is joining us right now. So as Doug shared, I'm going to be speaking on Maxwellian mirages in general relativity. And if anyone has a question or comment at any point, by the way, please don't hesitate to go ahead and speak up right, even in the middle of the talk. I welcome that because I really enjoy the interaction. I'm not necessarily on a strict agenda to get through everything. I certainly have plenty enough to keep us occupied for the colloquium duration, and I'll try to get through all of it efficiently, but I love questions, so please don't hesitate to ask any question at all. So with that said, I'll give you a little outline of what I had in mind. I'm going to look first quickly at what I'm referring to here as naive gravito-electromagnetism, and this is in fact where we see mirages, as we call them, commonly occurring in the literature. We'll expose some of those mirages right off the bat just by stating what they are and why they are incorrect. And then we'll move into a little bit more of a formal demonstration that those in fact are mirages. And we're talking about mathematical predictions that often appear in the literature about gravity that are incorrect. And so what we'll do in step 3 here is we'll formulate what I'm referring to as a gauge invariant or coordinate invariant gravito-electromagnetism. And there's some new content here that actually extends a little bit beyond the paper that Lance and I wrote together. But I bring it back to the content of the paper with this item 4 here, where I talk about the so-called Coulomb, or sometimes called transverse gauge or coordinate choice, and contrast that with the harmonic coordinate choice that is discussed initially in step 2 here. Then in step 5, I'll mention a quick application to superconductors. There's been some email exchanges between a number of us who are here in the meeting concerning some recent papers, in fact, involving gravito-electromagnetism and their interaction with superconductors. So I thought I would just throw in a little blurb here. Maybe it'll be like the last 10 minutes or something like that. I'll try to manage time in such a way that we can get to that. All right, so I will have some introductory slides here if some of you can bear with me. I just want to, as best as I can, have everybody on the same page. I know we have a diverse audience, some grad students all the way up to very seasoned professors who've been doing this many decades. So I'm going to do my best to try to offer some slides that kind of familiarize everybody with what we're talking about, and then get into the more nitty-gritty math that maybe only some of us will be able to follow closely. So as it states here, it all begins with the first ingredient, which we call the metric. And I'll describe that in a little bit more detail, but here's kind of a roadmap of GR. I call this my GR in a nutshell slide. You take your metric and you apply some derivatives. So think of the metric as almost like representing the gravitational potential. You take some derivatives and you construct what's called the Riemann Tensor, which tells you about the curvature of space-time. From there, you also can construct or contract what we call the contract indices to form the Ricci tensor and the Ricci scalar. So those two pieces here, the Ricci scalar and the Ricci tensor together, are pieced together to produce what's called the Einstein tensor. And it's the Einstein tensor that's related to what's referred to as the stress energy momentum tensor. And Einstein's genius, of course, with others I'm sure who participated in that work to develop general relativity, arrived at this one compact, beautiful equation here. Capital G mu nu, the Einstein tensor, is proportional to the stress energy tensor T mu nu. So if nothing else, at least this slide lays down some of the notation that we're going to be using, although I'm not going to define in further detail what these Greek indices and such refer to, since of course it would take us into a bit too much of a digression of what how to learn GR. But I'll do my best as I go along. So the space-time metric, if anyone has seen in special relativity, could be written like this. It really should be written as a differential, but just to keep life simple, just trying to point out, it looks kind of like a Pythagorean theorem in a sense. You've got the x squared plus y squared plus z squared, but then you have this extra term here at the beginning, this negative c squared t squared. And you could think of the coefficients in front of these four terms as being written down along this diagonal here. So as you can see, I'm already pointing out the signature I'm going to be using, which is a negative 1, 1, 1, 1. And in fact, that the 0, 0 element here will be the time, and the remaining three elements here will be what we call the space elements of the metric. So this is the Minkowski metric. And then for those of us who are familiar with linearized GR, we introduce the metric perturbation h mu nu, which we consider as very, very small compared to 1, so that it's just essentially a small perturbation to the Minkowski metric. So visually speaking, you could think of h mu nu as kind of representing the gravitational field on a flat space-time background. So this is where we kind of use a little bit of sort of differential geometry mixed with field theory, and we kind of move back and forth between the two of them. So we're going to think of h mu nu as like a field, and in that sense you could imagine it basically perturbs space-time in such a way as to cause, in this case it looks like dynamic ripples on what would otherwise be flat space-time there on the left. So I'd like to offer some intro slides on the idea of gauges, invariance, and transformation. So bear with me here a little bit. This is a cute little slide I made here with Einstein. And I figure that we're going to be using this terminology gauge and coordinate transformation and invariance. And so I'd like at least for all of us to have some sense of what we're talking about when we use those words here. So you could imagine, for instance, if you set up a coordinate system that's going to measure Al's height, you could choose the bottom here to be at y equals 0 and the top of his head to be at y equals 6 feet, although it turns out he's 5'9". I looked it up, but anyways, you get the idea. And the whole idea here is that you could measure Al's height by taking y final minus y initial and find, of course, that he's 6 feet tall. Now here is what we call a coordinate transformation. We could choose to shift the origin, say like to his midline, and then identify that now his feet are at -3 and the top of his head is at +3 feet. Now notice Al's height is still going to be found by using now y prime final minus y prime initial, and you get the same result there, which is the 3 feet, looks like I have a typo there, ignore that L, minus a -3 feet equals 6 feet. So the point I'm trying to make here is, do you notice that by us shifting the coordinate system, certain things changed, namely the coordinate that we say his feet is at and the coordinate that we say his head is at, that changed, but his height remained the same. So we could refer to Al's height as a coordinate invariant quantity, meaning it doesn't matter what coordinate system you use, his height will stay the same, at least in this very, very simplistic context of what we're talking about. So as I was saying, I hope this gives everyone a sense of what we mean when we say that something's invariant under a coordinate transformation. It just means that when you change your coordinate system, that quantity that we were talking about, which happens to be Al's height here, stays the same regardless. So a gauge can be thought of as a coordinate system, and this is where we're going to use those terms interchangeably. There's some individuals who are very staunch about what word you should use when you're speaking in terms of general relativity. I will be honest that I'm very loose. I will use coordinate and gauge interchangeably. And so, of course, I already showed you an example of what a transformation could look like going from the y coordinate system to the y prime coordinate system, and the invariant that you have, which is a physical quantity that doesn't change under a gauge transformation. You can also do the same in electromagnetism, so this is relevant, again, in the context of what I'll be talking about here. Now, in this case, I'm going to start with a battery, and imagine it's like a 12-volt battery, and you hire this guy to measure the voltage, and he says, okay, I'm going to connect two probes here to the two sides of the battery, one's negative and one's positive, and if we assume the negative side is at 0 volts and the positive side is at 12 volts, he could take a 1 ohm resistor, let's say, and he could find that he gets a current of 12 amps. But notice that the label on the battery says never ready 500. So he's going to advertise this thing as having 500 volts on one of those terminals. Well, that's fine. Put 500 volts there. As long as you put 488 over on the other terminal, then you find that the current still turns out to be 12 amps. So in other words, we're seeing here in the context of electromagnetism, again, you've got this idea of certain quantities are gauge dependent, like the voltage here, and certain quantities are gauge invariant. So he's puzzled by this, but we know what's going on. We know what's happening is that the current is an invariant quantity under what we could call a potential transformation. So we changed the two values of these terminals in such a way that the current stayed the same regardless. So it makes no difference what you want to label these two terminals. What you're looking for are invariant quantities. So I'm a big proponent that when we're working in general relativity, I think our best bet is to look for gauge invariant quantities so that we know that they are something we can rely on, that all observers would agree upon regardless of their coordinate system. That's kind of the moral of the story here. So with that said, we can say that in this context, a gauge can be thought of as a choice of potential or energy scale, and a transformation is just changing from one voltage to another. The invariant in this particular case, which was the electrical current, is a physical quantity that didn't change under a gauge transformation. All right, so now let's get into what we are familiar with electromagnetism. We know we have our Lorentz force, we know we have our Maxwell field equations, and we have this is the part here that I want to emphasize. We have our electric field and our magnetic field as gauge invariant quantities. And the reason we know they're gauge invariant is because the gauge freedom in electromagnetism can be described this way. You've got your magnetic vector potential, which can be changed by the gradient of some scalar quantity, and you've got your electric scalar potential, which can also be changed, in this case, by the time derivative of that same scalar quantity. What you can show then, which of course I won't do here because of time constraints, is that if you transform this electric field and this magnetic field using these gauge transformations down here, they stay the same. So we say that the electric field and the magnetic field are gauge invariant quantities that all observers would agree upon in the context of this gauge freedom.
Nathan, you might note they're not coordinate invariant though.
Absolutely, thank you, Lance. And I was thinking about it in the back of my mind, and I wasn't going to say it unless someone else said it, and you are absolutely right. So I should emphasize that gauge invariance here, or I should say these quantities being gauge invariant quantities, is restricted to the gauge freedom denoted by the gauge transformations at the bottom of the slide, not by the coordinate transformation that I talked about when we were measuring Al's height earlier. Thank you, Lance. All right, so in linearized GR, what you can do is write down in fancy notation the very thing we did when we were measuring Al's height, which is you can change your coordinate system from an x coordinate system to an x prime coordinate system. Now the mu here tells us that this can be done to both space and time. So if you want to think of it as like spatially you could shift your coordinate system, and temporally it's like you could cause your clock to be shifted by some amount, like shift it forward an hour or backwards an hour, for instance. Now it turns out that the metric perturbation that I described earlier as a perturbation to flat space-time turns out to transform according to the equation shown here in the context of linear GR. In nonlinear GR you pick up one more term. So here notice that this xi, which is this squiggly looking Greek symbol here, is showing up here with derivatives. So the point is, of course, in linearized GR, you have gauge freedom, as we can call it, in the metric perturbation. Now, this is analogous to what you see in electromagnetism, where A mu, the 4 vector potential, also has gauge freedom, as I described on the previous slide, but now written in a covariant notation. Now, a common gauge choice or coordinate choice, like I said, I'll use those interchangeably, is what's called the harmonic gauge. And so what we do is we find that the 4 derivative, in other words, partial derivative of mu, acting on this h mu nu, there is a bar above it, and that refers to what's called the trace reversed metric perturbation. I'm not going to bother detailing that here, only because I don't want to get bogged down in too much nitty-gritty, but you can simply see that it's very analogous to the Lorenz gauge in electromagnetism. So anyone in graduate E&M in that lovely 220 class would probably have seen this, and will thank Doug later, if not now, then later, that they know what this means. So notice there that the two gauge choices for the metric perturbation and for the 4 vector potential have the same form. And this was very suggestive to physicists because it leads to a wave equation here. The Einstein field equation now is a wave equation, very analogous to the Maxwell field equations, which are also a wave equation in the Lorenz gauge. So everything looks very nice. It's all so symmetric in the sense of GR and EM looking so similar that a lot of authors unfortunately ran away with this without looking carefully at the nitty-gritty. And it's led to some significant issues. It's not just a subtlety. It's not just a small minor detail. It leads to major errors in predictions about how gravity will work. Here's how usually the formulation goes. You define what's called the gravitational scalar potential, which is in terms of the time-time part of the metric perturbation, and a gravitational vector potential, which is in terms of the time-space terms of the metric perturbation. And then you can even go as far as even writing down a gravitational 4 potential if you want to. Only in the formal sense of taking this scalar potential and this vector potential and shoving them together into a 4 vector. I'm not talking about transformation, whether this thing transforms properly, for anyone who might be thinking about that. Now, we can take the ideal fluid stress tensor, which is the usual way this goes, and if we want, we could look at relativistic dust, so kill off the pressure terms, those capital P's, and reduce these velocities to just 3 velocities, and turn your little gamma, the Lorentz factor, to 1. And in that case, you've got, of course, your rest energy density, your momentum density, which we could write as a mass current, so there's that J, capital J, kind of bringing us toward an electromagnetism type analogy, and then we'll set the stress part to 0 in the non-relativistic case. So this is standard procedure in the literature among many papers. I'm just laying down the framework here. And we can write down, even if we want, a mass 4 current density, again, just to emphasize the analogy with electromagnetism. In that case, you can even write down Maxwell's field equation in a form that looks literally identical, practically, to electromagnetism. And this is where issues arise. So far, we're fine. As far as I'm aware, no errors, no problems, no mispredictions. It's right around this point where things start to go haywire, which is, if you go back to your metric perturbation, you'll notice we're focusing our attention here on just the diagonal and the horizontal first row there. And we're going to write ad hoc, I emphasize, ad hoc, in the sense that we're going to define a gravito-electric field and a gravito-magnetic field in a manner that's similar to electromagnetism. But remember what I emphasized earlier. In electromagnetism, we arrived at an electric field and a magnetic field via constructing a gauge invariant quantity, so that the battery tester guy, when he goes up to the battery, he always gets the same electric field no matter what you do to the voltage. That's not true with these gravito-electric and gravito-magnetic fields. They can be shown to have gauge freedom. So this is already where we see a red flag, but unfortunately in the literature it's often overlooked. What happens next is, taking these two fields, I should mention, they do have legitimacy. They aren't just completely random or arbitrary. For instance, the Earth drags space-time in a direction of rotation about its axis, and this is often called the lensitarian or gravito-magnetic field, and it's even been measured by gravity probe B, and probably perhaps I don't know all the experimental history, but it is a real thing as far as we're aware. And so in that, it's there's a gravity probe B uses like a line of sight detection, and that deviation demonstrates that the gravito-magnetic field is a real thing that the Earth generates. However, the issue is this. Oftentimes in the literature, authors will simply write down the Maxwell equations identical to electromagnetism just by virtue of the analogy. And already at this stage, we'll find that there are problems, that if you do this formally with GR, you don't actually arrive at these exact equations that you see here. and I'll point out what the issues are. Now, while we're at it though, let me mention that we have this gravito-electric permittivity of free space, this epsilon sub g, playing the same role as you have in electricity, and you have this gravito-magnetic permeability, also playing an analogous role as the permeability in electromagnetism. But notice that the 1 over epsilon g is 10 to the minus 10, while the mu sub g is 10 to the minus 27 in SI units, and that's why gravitomagnetism is so weak and so difficult to measure. Now you can also go to your equation, your force equation, and you'll find that you get something also similar to the Lorentz force, but it's a gravitational version, comes out of the geodesic equation of motion. Now I should mention there's a factor of 4 there. It bugs some people, and if you go through the nitty-gritty, you find you cannot get rid of that factor of 4 unless you move it to in your definition of your fields. It'll rear its ugly head over in the field equations. You can't get rid of it. If you get rid of it in the force equation, it's going to show up in the field equation. Now, what I call ultra-naive formulations even omit the factor of 4 because they just love the analogy so much that they ignore the fact that there's just factors in there that don't line up. So I'm referring to this whole slide as naive gravito-electromagnetism because there's an assortment of issues. And I'm just going to kind of nail them, just state them, and then I'm going to go back and show the nitty-gritty of why they are errors. First is that in that non-relativistic approximation that we used, we can show that there is in fact no Faraday-like law for gravity. You can show actually what happens is it's the gauge condition that appears in linear GR. That gauge condition in linear GR has more constraints than the gauge condition in electromagnetism. And those additional constraints are often overlooked, and it's those constraints that actually eliminate the Faraday law. Furthermore, it also seems to appear in this formulation like all the degrees of freedom are radiative degrees of freedom, in other words, involved in gravitational waves, when in fact they're not. You can show that it's only the quadrupole sources, Tij, that radiate. So if you kill those off, which we did earlier, if you noticed, we killed off Tij, then you've killed off gravitational wave emission or radiation. So what that means then is yet another mirage is to think that there are 3 vector gravitational waves, and they do come out of the math. I'll point out, these equations come out of the math, but you can show that they're faulty. And the reason it turns out that they're faulty is because if you bring the gauge condition back in, you find that it interferes with the actual radiation of gravitational 3 vector waves. What I mean is this: if you expand this out in terms of the metric perturbation and you bring in the gauge condition, you discover that the real radiative degrees of freedom are not there. I'll just say it like that in a sentence because trying to do more would require a lot of math that I have to kind of share. Now this is, in my opinion, a very, very important point, which is this. These gravito-electric and magnetic fields have gauge freedom. They are not gauge invariant quantities, which means if you transform into an appropriate coordinate choice, you can make them vanish. And if you can make them vanish, then it means that not all observers would agree upon them. And so for that reason, I believe, is probably one of the most relevant to being suspicious about these fields. So it's due to them having been constructed as ad hoc definitions, not constructed as gauge invariant quantities.
Nathan,
Okay. Yeah.
Would it be fair to also remark at this point that there are no gauge invariant forces in gravity?
Oh yes,
either?
I will absolutely scratch that itch too, Lance. You better believe it. I'm going to hit that also. And so when we get to that slide, bring it up again because I think then we'll have the equation sitting in front of us and we can point at it and talk about that.
Yeah.
I would like to mention this though. Notice that in this gauge condition here, we've ruled out gravitational waves that actually appear in the center section of the metric perturbation if you're talking about gravitational waves propagating in the z direction. I wanted to show this slide just to bring to our attention that there is a commonly known transverse traceless gauge, commonly known, and that's the gauge typically used to describe gravitational waves. And for a while I was puzzled by these 2 gauge conditions seeming to be at odds with each other. I mean, notice for instance, for a gravitational wave that has what's called cross polarization, here in the harmonic gauge it seems to be 0, whereas here in the transverse traceless gauge it's non-zero. And so there seemed to be a discrepancy there. And that was one of the main reasons I studied this topic, in fact, because I'm actually more interested in gravitational waves than anything else, but gravito-electromagnetism is interesting as well. But I'd like to just kind of give you a visual what this H sub plus and H sub cross are. They are the gravitational waves with plus polarization and cross polarization, and we'll come back to these quantities H plus and H cross right up near the end of our talk. So keep this picture in mind, that this is yet another gauge. It's actually a subset of the harmonic gauge. It's a more restricted gauge. And what it leads to is this. This is what puzzled me the most when I studied this during my PhD, is that it's directly evident from the Einstein equation that if you pick this gauge, which means you're setting the H00 quantity to 0, you can see immediately that that's going to cause your T00 stress tensor component to be 0, which means this only works in vacuum. And my personal research interest was in how gravitational waves interact with matter. And so if you use this gauge, you eliminate the ability for gravitational waves to even interact with matter. All of this will be resolved when we write down a gauge invariant formulation. So these are all puzzle pieces just to show the landscape of where all these problems lie and how I believe they can be resolved if we just take a gauge invariant approach. All right, so that's kind of a segue into this new approach. And so we're going to apply what's called the Helmholtz decomposition theorem, which is just a fancy way of referring to how you can decompose a vector or a tensor into what are called irreducible parts. And it will equip us to construct gauge invariant quantities. When we do that, we can eliminate all the mirages of, I should really write 3 vector gravitational waves, and reveal the true radiating degrees of freedom. And then to kind of wrap it up, I'm going to loop back to a particular gauge or coordinate choice called Coulomb gauge or transverse gauge. Different textbooks use different names. Poisson and Will use Coulomb. Carroll uses transverse. At the end of the day, the math leads to the same thing, which is that you can write down a formulation of gravido-electromagnetism that is a little bit cleaner in a sense, and I'll show you what I mean by that, but unfortunately you lose the gauge invariance. And so I must admit that personally I like to stay in the gauge invariant formulation, but this Coulomb gauge still is nice for the purposes of having, in my opinion, what is a simpler, cleaner formulation mathematically at the expense of losing some losing the gauge invariance. And I'll spell that out here shortly. So first let's write down the metric. So we're still in linearized GR. We still got Minkowski plus a small perturbation. We're going to write down the perturbation like this though. H00 is going to be the usual scalar potential with some prefactors there so that you recover the usual Newtonian gravity. H0I is going to be broken up into 2 parts, a transverse part and a longitudinal part. And then Hij is going to be broken up into even more pieces. This capital H is the trace, and forgive me, my notation differs a little bit from the paper that we used, that Lance and I wrote, and I'll explain the differences when we get there. This lambda is another quantity that's what we call the longitudinal traceless part. So it's traceless because if you take the trace, these 2 derivatives are going to cancel with these 2 derivatives, and this thing's going to vanish. This epsilon is a 3 vector, but there's a symmetric derivative here that causes this thing to also be traceless. And lastly, this last piece is, of my personal opinion, the most interesting. It's the transverse traceless part of the metric perturbation, and it's in fact where gravitational waves live. So out of all this madness that you see here, this last guy in the end is gravitational waves right there. Now these are the constraints that I just described in words, namely that beta is transverse, epsilon is also transverse, and Hij tau tau is transverse. In addition, Hij tau tau is traceless. So here's all the math to describe what I had in words.
Yeah, and Nathan, you should say, just to ram it home, you haven't done any physics yet. You've just reparameterized.
You are right.
So, you've introduced a whole bunch of new variables, but and then constrained them with the new equation. So if you add them up, you've actually got like 17 parameters for the 10 components of the perturbation. And then you've got like 7 constraints below to tie them all back in. So it can be, you can feel like you're kind of getting your pocket watch taken here, but so far no physics. Yeah.
You're absolutely right. Lance is awesome at counting degrees of freedom, and he always takes care of that for us because I get lost. But yes, the 10 degrees of freedom of that metric perturbation are all here. And like Lance just pointed out, it seems like we have more information here, but then the constraints clean it all up to bring us back to the 10 again. And you're right, no physics yet. That is yet to come. So this was done in Flanagan and Hughes, by the way. This is not credit to me by any means. And in fact, Poisson and will do it again in their textbook. What we did is we elaborated upon it and showed that in what I would refer to as true gravito-electromagnetism falls out of this formulation. So here's kind of how the machinery works. You go back to the linear transformation equation that we already discussed earlier. You use that metric I wrote on the previous slide, and you write down this Xi gauge 4 vector, which represents the coordinate transformation. You write it in a time piece, comma, a space piece, where the space piece is also broken up into a transverse piece and a longitudinal piece. All of that is for the purposes of applying what's called the Helmholtz decomposition theorem. When you crunch through the gory details, which I'll spare you of, you will find that this metric perturbation, this metric that we wrote down here, I wrote it again here just to point out. I'd like to emphasize where some of these pieces are going. I think it'll be helpful to see. What we often think of as the Newtonian scalar, notice is showing up right here, right? And then notice that over here, we've got this alpha and this lambda also showing up here and here. And then coming back over here, we've got beta and this epsilon that are forming what you could think of as the new vector potential. So think of this chi as the new gravito vector potential, but remember it's coordinate invariant, unlike the other one that we saw earlier. And then notice also you have this other trace of Hij, as well as the lambda playing another role, so lambda doubles up, and you construct this theta here with those two guys. And then lastly, Hij, interestingly, is a very unique fellow. It turns out Hij, which is a metric perturbation component, is in fact gauge invariant all by its lonesome self without having to play with friends, just by himself. So these are the 4 gauge invariant quantities, which you could think of as gauge invariant potentials. But I just want to emphasize that...
Nathan,
yeah.
Why is there 11? You've got 11 of them.
11 of what?
11 potentials.
Are you referring to, when I refer to potentials, so this is where verbiage can get a little bit tricky. When I refer to potentials, I'm talking about these guys right here.
Oh.
Right? Under the constraints. Don't forget the constraints still there. So remember, Hij is constrained by being traceless and transverse. And
sorry, I didn't mean to divert you.
No problem.
Yeah, you're fine. You're fine. I didn't mean to delay you or divert you. Go ahead.
No
you're
problem
fine.
at all. It's probably helpful to everyone. So I'll just point out chi is still transverse, by the way, because both of these guys are transverse, each in their own right. So the bean counting all works out at the end if you count it all up. All right, so Lance is a big fan of, well, I hope I'm speaking properly on his behalf. He's a big fan of using the force equation versus the field equation to identify fields. And so in his honor, I took that approach. Honestly, I'm fine going either way, but I went the approach of the equation of motion. And the whole idea is this. If you write out the equation of motion, I know this looks like a bit of a gory mess. I didn't know how I could write it any cleaner, but I think you'll see some familiar guys in here. Here you have, of course, your gradient of a scalar potential minus time derivative of a vector potential. So that's very suggestive, obviously, right? And then, of course, you've got the velocity crossed with the curl of a vector potential. Obviously, very suggestive as well. In fact, it harkens back to the very first title slide with the picture where you saw that Lorentz-like force, where you had a gravito-electric field and a velocity crossed with a gravito-magnetic field. So that's still emerging. But notice we have other stuff coming out here too. That theta potential comes in as well. And lastly also, notice Hij tau tau comes in with a time derivative on this term, and then with spatial derivatives over here on these terms there. Now, there is one last piece of the puzzle here, which is this guy here. And that chi at the end there is what I'm going to call a gauge vector. It's all the leftover stuff that remains in the equation of motion once you've rearranged. I had to do a lot of rearranging, kind of, it seems a little artificial, but I had to move things around in such a way as to get all the gauge invariant guys to sort of conspire to become Lorentz-like in that first line, and conspire to build the theta and the Hij. Well, the Hij was just sitting there, but conspire to build that theta. All the leftover junk is this chi at the end. And the way I physically interpret that is that because all the other quantities are coordinate invariant, which means all observers will agree upon them, this chi is what's responsible for the equivalence principle. In other words, it's because we're now looking at the force equation or equation of motion, there must be something that allows the equivalence principle to cause the overall force or acceleration to vanish in an appropriate coordinate system. If we did not have such a thing, then we would find that there is a contradiction with the equivalence principle. So I think this was what Lance was asking about. And keep this in mind. This chi, let's remember that chi. Remember this chi here, because we're going to come back to this. We're going to figure out a way to make it go away, but we're going to pay a price some other way.
Nathan, I would just say to rephrase it, another way to rephrase it is that there are no gauge invariant forces.
Yes.
In gravity. So
excellent point. That's exactly what makes the geodesic equation of motion different from the electromagnetic Lorentz force. Absolutely right. Yep.
Thank you.
All right. So here's the new stuff. New in the sense that I haven't seen anybody out there write this, and I must have seen at least a couple hundred papers on gravido-electromagnetism. So I just thought to myself, why would we not write down a gauge invariant gravido-electric field and a gauge invariant gravido-magnetic field using these gauge invariant potentials? Now notice that because we have a phi scalar potential and a theta scalar potential, both of them are going to have gravido-electric-like fields associated with them when you take the negative gradient. Now, you might wonder, how do we know which one we should tack on the negative time derivative of chi? And I'll go back to the equation of motion to remind you, it's because this appears here at the beginning. You don't have any term here that has just the gradient of theta. That doesn't appear anywhere here. So I just simply identified that that would naturally be the scalar potential associated with the gravido-electric field with phi is the one that would have this minus chi on it, whereas the gravido-electric field with theta would not have the chi in there. In other words, going to the Newtonian limit, we would keep, I'm backing up to the previous slide, we would keep only this guy here in the very Newtonian limit and not the one with theta. So with that, I also defined some new fields which I refer to as the propagating gravido-electromagnetic fields. They are tensor fields, and so I wrote them with the swirly notation just to try to emphasize the distinction from the 3-vector gravido-electric field and the 3-vector gravido-magnetic field. These guys are involving the Hij tau tau, which we also said is gauge invariant as well. And the definitions with the negative time derivative and the positive spatial derivative are very similar, analogous to what you see in electromagnetism with the vector potential. So with that, the equation of motion becomes this now. You've got your Lorentz-like force, E plus V cross B, and then can't do anything about this theta dot, sorry, because as you can see, of course, there is no gravido-electric field that we can replace that guy with. It's just how it is. This guy, however, though, has an analogous term in electromagnetism. I didn't write it down in our set of slides, but if you write down the relativistic Lorentz force in electromagnetism, you will also see that there is a term involving a velocity dotted with the electric field. So that's actually analogous there. And then you have other terms, and I couldn't get swirly in here, so you'll have to forgive me for my lack of PowerPoint skills. I was able to get swirly up here because I used paint, but it was going to be too much of a pain to get swirly E and swirly B. So just realize they're the same tensor fields that I have in the boxed equation above. And notice the chi term at the end with the gauge vector there. So I'd like to emphasize the contrast. These new gravido-electromagnetic fields are gauge invariant because they're written in terms of gauge invariant potentials. in contrast with the gauge-dependent gravito-electric and gravito-magnetic fields, which the vast majority of the literature works with. All right, so let's build, now we can do some physics. If we want to call field equations physics, here it is. So I want to emphasize all that we've done so far was, I mean, you know, it's arguable what exactly, I guess, is physics, but we've only looked at gauge freedom and gauge invariance. Now we bring in the Einstein field equation, and you find that the Einstein's field equation leads to these three equations. You've got the space-space, the space-time, and the the time-time, the space-time, and the space-space. So the time-time turns out to involve theta. The space-time here involves theta dot and chi, and then this nasty looking equation at the bottom here is all of your space-space. The only thing maybe I'll emphasize here is that you might notice that the only wave operator in this entire set of maddening field equations is this guy right here, box of Hij tau tau. So you know gravitational waves live down here. We're going to do a little bit better job, I would say, of making this look Maxwell-like. But for now, what I'll do is I'll take those new definitions of the gravido electromagnetic fields that I wrote down, and I will start to clean up the mess a little bit. You can write down a Gauss law, del dot E. So that's basically your Newtonian gravitational, Newton's law of gravity. But then notice this guy over here, the del dot E sub phi, also, in a sense, is Newtonian gravity. Because what happens is in the Newtonian limit, you actually lose all of this stuff. And so you end up finding these two equations actually become the same in the Newtonian limit.
Nathan, are you still under the linearized gravity?
Absolutely. Thank you for asking, James. The entire talk will be on linearized gravity, but that's a great prelude to, we will do nonlinear, but not today. But yes, that's right. This is all under linear gravity still. Was there anything that you saw that seems to contradict that, or you're just curious?
Oh, it's just in the previous page, you wrote the like the general formula, and then underneath it, you wrote the linearized version.
Yes. Oh, I got you. Yes, you're right, because this looks like it could be full nonlinear. You're right. I probably should have written this with the box operator acting on h mu nu to emphasize we're still in the linear. Thank you for pointing that out. Now we also get a Gravido Ampere Law, and notice that the so-called kind of gravitational displacement current turns out to be acting on the E sub theta. Now right there alone with just these equations, you can see that you won't get 3 vector gravitational waves, because if you follow the usual recipe to get to wave equations, you're going to take the curl of this Ampere-like law, but notice what's going to happen then is that you're going to get a curl of your E sub phi here. And then when you go, maybe I'll get ahead of myself a little bit here. When you go to the Faraday-like law here at the bottom, it involves E sub phi. But the Ampere law involves E sub theta, which means you're not going to be able to combine your Ampere and your Faraday into a way that would allow you to arrive at box operator on either of those gravito-electric fields. And you'll have the same problem with the gravito-magnetic field. So the point is this. We already see that when you construct things in a gauge-invariant way, it eliminates the error of writing down 3 vector gravitational waves. So you got these 2 Gauss-like laws on the top. You got an Ampere-like law in the middle. You've got all this nastiness in the space-space equation. We haven't dealt with that yet. I promise you we will. And then you got your source-free equations that just come out of the definitions of our fields. Because if you just take the curl of your E sub phi, or the curl of your E sub theta, or your dot product of your B sub g, then these source-free equations fall out immediately. Now here's how you clean up the mess. Let me emphasize this nasty equation here, the one that comes out of the space-space part of Einstein here, that one can be cleaned up significantly. So this guy right here, you can clean up. And not only that, you'll find that along the way, you can actually get rid of this displacement current as well. So that's what's going to kind of happen next. But we're going to have to do a little bit of work, and I'll try to do this kind of swiftly because we have about 12 minutes left, and I want to make sure that we hit everything. So here's the idea. You write down a stress tensor that's also decomposed into irreducibles in the exact same manner as we did with the metric perturbation. You got the time-time piece, you got the space-time piece, which involves a transverse piece and a longitudinal piece, and then you've got your space-space part, which again involves a trace part, a traceless longitudinal part, a traceless rotational part and a transverse traceless part. So it's the same structure mathematically with the same constraints. The transversality of capital R, little r, and Tij, and the tracelessness of Tij tau tau. With those, you find that those field equations I had on the previous slide, the source equations, clean up to this. Now notice, we don't have that big, long, nasty equation for space-space anymore. Instead, here's what happened. We broke off the radiative degrees of freedom as their own separate equation. So gravitational waves now live exclusively in that equation right there. And then we still have our two Gauss laws, and we have an Ampere law, and we're done. So it's very clean, actually. It's very clean in that sense. And then, of course, you can still write down your source-free equations. They're identical. I haven't changed anything there at all. So what I would suggest then is that we take these funky rho tilde and r vector and p tilde and I dot, which don't represent anything physical at this point, and now we introduce the ideal fluid stress tensor, and we take the three components of the ideal stress tensor, and then we relate them to the Helmholtz decomposition stress tensor that I was using. When you relate them, you'll find that that rho tilde guy actually involves mass density and pressure. That r vector involves other such quantities, the p vector, and the Tij. So you basically get results for each of those weird stress tensor components in terms of more physical quantities: mass density, pressure, and velocities. And it turns out that for an ideal fluid, those other quantities, the capital I, the L, and the little r, they involve rotational type degrees of freedom. And so for a typical ideal fluid, you can eliminate things like involving vortices and such, and that's really the physical reason why those quantities are going to zero at the bottom. When you do that, then you find, one more piece of the puzzle that I think is interesting. Let's bring in those tensor gravito-electric and tensor the tensor gravito-electric and gravito-magnetic fields. You can then write Einstein's equation for the space-space part in terms of what I call a Gravido Ampere Law, but involving tensor fields. In fact, in vacuum, you can see it's very much like Ampere's law in vacuum, like in electromagnetism. So with all that said, voila, this is the pinnacle moment. Will the real GEM field equations please stand? And I would suggest to you that they are these. Of course, I mean in the context of linear GR. So some common errors that I was pointing out is that this term here is often neglected when people write down the Gauss-like law. But if you neglect that term, you actually kill off your Ampere-like equation here. That's one of the errors that often occurs. Another error that often occurs is to neglect the tensor part altogether, and that's where gravitational waves live. So you can't talk about gravitational waves if you're going to kill off the tensor part of the metric perturbation and the stress. And get rid of my annotations here. All right. So lastly, to bring it home with the paper that Lance and I wrote, I kind of started out with stuff that we did, and then I took a little bit of a detour, and now I'm coming back to what we did. We used what's called the Coulomb or transverse gauge, which is much like the Coulomb gauge in electromagnetism, except you apply that on the H0I, and you find that in that case it kills off the alpha, and you also apply it on the Hij part, and that's going to kill off the lambda and the epsilon. So it's a particular gauge choice now. And when you do that, you'll find that that gauge vector, which I encouraged us to remember, that gauge vector now is 0. So what that means now is that when we go to look at our previously gauge invariant quantities, when you kill off those particular terms, those gauge invariant quantities clean up very nicely, but they're not gauge invariant anymore, because only this top row is gauge invariant. If you kill off lambda and alpha and epsilon, what you're left with is now gauge dependent. And these these gauge invariant gravito-electric and gravito-magnetic fields are now going to look cleaner, but they actually reduce to what you find like in Carroll's book, to this row here, but those now have gauge freedom. And here's the explicit gauge freedom. Oh, actually, I'm sorry. Let me mention, this is this box here at the bottom is just to connect back to the notation that you'll find in the paper that Lance and I wrote on Mirages. So I just wanted to emphasize that what I've written here if you want to read that off in the Mirages paper, it's just going to look like this instead. And so instead of speaking of E sub phi and E sub theta, we just spoke of E sub g, and we wrote a new name called the N field, which Lance was so gracious as to name after me, evidently, and but then again call it the neutral field. So note that these two boxes are related to one another there in our Mirages paper. Also, we speak of an Sij, which can be related to what we have here in these slides this way. And so our Sij now, notice if you're going to kill off your lambda and kill off your epsilon in this gauge choice, then Sij becomes the same as Hij tau tau. In other words, Sij becomes your gravitational waves in that gauge choice. When you do that, and so here's a beautiful table Lance produced at the end of our paper where you can see the difference between transverse coordinates and harmonic coordinates in the two columns there. So I kind of grabbed this out of our paper and figured I'd throw it in here in case anyone wants to talk more about what the equations we had in our paper. But I want to finish off with this important connection. Going back to the equation of motion, remember, in that Coulomb gauge, what we did is we killed off this chi vector. So then someone might say, well, wait a minute, if you killed off that chi vector, didn't you get rid of the equivalence principle? Not so fast. The equivalence principle will now be hidden in the gauge freedom of these gravito-electromagnetic fields up here because you disturbed their gauge freedom. They are no longer gauge invariant quantities anymore. In fact, you can show explicitly that the gauge freedom based on this linear transformation here can be shown to be like this. Remember, capital A, capital B, and capital C are coordinate information, which means now phi has coordinate information, theta has coordinate information, chi has coordinate information, and Hij tau tau has coordinate information. So now all the coordinate information is just hiding in the fields themselves instead of appearing explicitly outside in terms of what I used with a chi. And lastly, this is pretty though, I must admit. Lance brought this to my attention, which is that in this gauge choice, what Poisson will call Coulomb gauge and what Carroll calls transverse gauge, your metric perturbation can be written in terms of the capital phi, the capital theta, the xi, and the h plus and h cross. Those are gravitational wave fields. So it's very beautiful in the sense that you see your two scalars along the diagonal, your vector potential along the horizontal, the top row, and your two gravitational wave polarization fields appearing all in one nice pretty matrix there, a matrix for your metric perturbation. Now, I did review a paper recently, and I was very happy. I considered this a small victory, so I wanted to kind of celebrate this a little bit. I was asked to review this paper, Neutron Star as a Mirror for Gravitational Waves, and I can say that prior to reviewing the paper, I saw this and cringed. After reviewing the paper, I saw this and smiled. So it sounds like reviewers are paying attention to this issue. Now, there's other stuff in here. This equation 2 and 3 get into more material that I've studied in the past that I'd love to share in the future. Maybe we'll write more papers and share this in future talks. But it's that top equation right there, boom. That made me happy because they're writing gravitational waves in linear GR properly instead of trying to write 3 vector gravitational waves with equations 1 through 4 there. All right, so I will stop there. There was, as I mentioned, there was that one last topic that I could mention if no one has questions, which is the application of gravito-electromagnetism to superconductors. But I will leave that there. If somebody would like to know more about it, I can talk about that, or I could just answer questions from what I already spoke on.
I would like to know about it.
That's fine. So I do have some questions, but I'll defer those till the end. So this is the time for questions, guys. If you have any questions.
I do have a question, but I also like to give it 0.5.
Wait, so no, go ahead, James.
Okay. So with your E sub theta, would it be possible to incorporate the temporal component as well to make it more symmetrical with the E sub phi?
So you said, can we incorporate which component?
So you go back to first. This is the first time you defined E sub theta.
Yeah, Lance and I have never seen this definition for a gravito-electric field in the literature. We wrote it as an n vector.
Yeah, so could you incorporate could you E sub phi, you have a time derivative component. Would you put in a time derivative component in E sub theta so that when you write it out in as A as a function of that, it would look more symmetrical with E sub phi?
Oh, I see. Do you mean like insert it in here
Yeah,
and just ensure that everything remains consistent when you do that?
yeah.
You know, I
In that,
think where you will
in this
run
case,
into
like,
problems. Oh, go ahead, James. I'm sorry.
in your A equation on that same slide, you may be able to get rid of the previous slide that you're on.
Oh, sorry. This one here?
No, the one with the A equals blah blah blah.
This one here?
Yeah. So you may be able to get rid of the third term and have that as a incorporated. Oh, the third term in the A in your bottom equation.
Ah, this term right here.
Yeah. If your E sub theta was also the time derivative component as well.
Well, you know, I think what's going to happen, James, so there's a balance between do you want to accommodate the force equation or equation of motion, or do you want to accommodate the field equations? And there's a bit of a tension there between those two, was one of the things Lance and I looked at quite a bit. And so I'll mention this. Notice that with the field equations over here, that you're going to run into some issues if you attempt to take these field equations, which at this point, by the way, nothing has been chosen arbitrarily as far as how to define the fields. Only the potentials are gauge invariant. And what's going to happen is if you try to go here, I think you're going to have problems with that first Gauss law right there. Because if you defined this with a time derivative piece in it, I think this Gauss law right here isn't going to be, you won't be able to write it down. I think that's what would happen. I just want to make sure I understand what you're saying. You're asking, can we add in a time derivative part on this guy here? True?
Yeah.
Yeah, I think we would have. Oh, by the way, I should also mention, chi is already a vector. Theta's not. So we would have to put in a gradient of a time derivative. And I think that would definitely introduce some issues there. I probably have to think about it more, though, James. To be totally honest, that's a question that, for me to be able to answer well and with confidence, I probably have to write out the math and think carefully about what you're asking and do it carefully so that I don't throw an answer out there that is not well thought out. You know what I mean?
Yeah. I do have another question. So if we were to rederive my gravitational Casimir effect, the gauge invariant, do you know if that would change anything?
Yes, I do have a really good idea about that, James. So, do you notice here that the gravito-electric and gravito-magnetic tensor fields can be used here to write down an impedance, a gravitational wave impedance. And that's going to involve, now, mind you, notation, I apologize, gets a little bit cumbersome here. This mu sub g is a little different from the, well, actually, no, this mu sub g is the same as what we've been using in my talk so far. And then what you would do is you would find a phase velocity. And from the phase velocity, you could then arrive at reflection and transmission coefficients. And then from there, you could proceed. Now this, for a thin film, which is I think what you would care about for the gravitational Casimir effect, I think it's this guy right here, the reflectivity for a gravitational wave incident on a conductor. And then the burden at that point would be these parameters, this eta sub g and this mu tilde sub g. Those are parameters associated with the particular material you're working with, like if it's a normal conductor or a superconductor. And then from there, you'd have to start looking at free energy density and such, which would take us into quite a tangent as far as this talk is concerned. So as a kind of a quick answer to your question, I would say that this is the formulation. Do you see how it ties in with what we're doing, though? in that the tie-in with what we were just doing in this talk right now is right here. A gravitational impedance using the E sub ij and B sub ijk could lead you to an impedance and hence a reflectivity. Is that addressing what you're asking there?
Yeah, sort of, except the part, so in my derivation of the gravitational Casimir effect, I didn't go into the actual like impedance value that you're talking about here. For me, it was just a parameter, which then I use other models to get. But the actual general form of my formula, because I derived it from the non-gauge invariant general equations. I don't know if it would change if I used your gauge invariant formulation.
Yes, James, I think I've studied your paper very, very carefully enough to know that, by the way, are you referring to this particular paper or the more recent one? This one here? If you're referring to this one here, James, my understanding is that when you used the results that that my advisor, Professor Raymond Chow, developed in his paper, in a sense, his paper, what it does is it effectively chooses this parameter here, this mu sub g tilde, as if it is so large that it basically causes this whole term to become zero, and the reflect. Go ahead.
I understand that part. I know that part definitely changed, but I had a formula which was more general than that, which was, is this prior to using any of Ray's stuff?
I know what you're talking about. So the approach was using the Weyl curvature tensor to write down the symmetric and anti-symmetric parts of the Weyl tensor as electric-like and magnetic-like tensor fields. Is that what you're referring to?
Yeah.
Yes, that would actually, in the linear limit, in the limit of linear GR, that formulation reduces to the one that we have here in this paper. If you want to go to nonlinear GR, then of course that's the calculation I have not done at this point.
Yeah.
Do you believe that linear GR is not adequate to describe the gravitational Casimir effect?
No, I think linear GR is adequate.
I think so too. And so if we both agree that it's adequate, that Weyl curvature formulation in your paper will reduce to this same exact formulation in the linear limit.
Okay.
Other questions? I have a question, but like, does anyone else have a question?
I have a comment. This is Sheldon. So, Nathan, I'm an independent researcher, former physics professor, and I live in Palo Alto. And I want to especially commend you for for the clarity of your presentation.
Thank you. I appreciate that. Thank you very much.
Also, Nathan, before I ask my question, so it was a very nice talk. You should, I don't know if you have time with the teaching, but the Pacific Coast Gravity is going to be in Arizona this year. You should present this there. Actually, I think it's an end of March or April. I'll have to go look it up, but it's at ASU, and I think they're still under pandemic rules. So it'll be no problem to go in that case. So anyway, but my question is,
oh, that's a good point. Yeah.
But my question is, one of the nice hidden symmetries in electricity and magnetism is dual symmetry, where basically, especially for sourceless Maxwell's equations, there's this duality between electric and magnetic things, right? So between electric and magnetic fields and so forth. Now, if you include sources, the fact that there are no magnetic monopoles kind of breaks that dual symmetry. But if you include magnetic monopoles, then now you have the dual symmetry even at the level of the sources in classical electrodynamics. So my question, my general sort of broad question is there some similar dual symmetry in GR, either with or without sources? So if you take all sources away, T mu nu completely zero, is there a dual symmetry? And then if you put in sources, is there something similar that would play the role of a magnetic monopole?
Oh, that's a great question, Doug. Thank you for asking that. So, from my exposure to the literature and our study on this, I found that the answer to that question actually differs depending on whether you're talking about linear GR or nonlinear GR, because the way that gravito-electromagnetism is written down in the two formulations is done so differently. In the case of nonlinear GR, I can tell you that the formulation, for instance, the one that James Quach was just talking about, that he referenced in his paper, they work, what's generally done is we work with the Weyl curvature tensor and we look at the symmetric part and the anti-symmetric part, and then the stress tensor is also decomposed in such a way that there is this electric-like charge density and magnetic-like, or excuse me, I guess mass density or energy density, and this magnetic-like energy density, and then there's this electric-like mass current and this magnetic-like mass current, and so the symmetry is very beautiful there, and so you get a result that looks a lot like what we have here. When my climactic final my climactic moment where I said this is like the set of field equations that I believe describes everything in linear GR. You get something like that, but you actually do get a source on the magnetic-like field equation, and you have a magnetic current. But keep in mind, those are tensor fields, so it's kind of up to you. So I could put it this way: if we're going to stay in linear GR, as far as I know, we don't get a magnetic-like source in the field equations. If you go to nonlinear GR and you work with tensor fields, you do have a magnetic-like source term.
Hmm. Yeah, so just some speculation.
But I should mention,
Okay, go ahead.
I was just going to say, but I should mention though that when authors write that down, by the way, it's a well-established formulation. It goes all the way back to Hawking and Ellis in their book on GR, where they are one of the first to write this down. I should just mention that it really is a mathematical structure that they are using to get the stress tensor to look like it's got a magnetic-like part and an electric-like part and so on. So I'm just trying to say that as far as the physical meaning, I'm not completely certain it would have the same physical meaning as in electromagnetism. It's just that you can get the math you can get the math there. It's kind of in a sense what this talk has done also. This slide that I have here, in a sense, I was just trying to get the math to look as Maxwellian as possible, but still be consistent with what we know is physically true. So I just wanted to emphasize that even in that context where the magnetic-like sources appears, I'm not quite clear what the physical meaning of that is. Maybe when we study that, and if we would be graciously invited to give another talk, like next semester or next year or something, I could probably answer that question better.
Oh, you're always welcome to come back and give it a talk. It makes my job easy. So actually, this is a really nice talk. So one final thing. So basically, within your linear context here, basically a divergence of B sub G equals 0. That's absolute. So you don't have a non-zero divergence for that. So that actually
yes,
that forbids monopoles, or the sort of equivalent of monopoles. So I wonder if you could, but you're saying in nonlinear GR, you don't have that restriction.
that is true. But remember, Doug, it's such a different animal that I don't even know if it's an apples to apples comparison. Because here, the reason why you have no, here the reason why the divergence of B is 0, it's because this chi right here is already divergenceless out the gate. Whereas in electromagnetism, A vector is not divergenceless out the gate. Here, this is like saying A vector is already divergenceless by construction. So there was no hope for the magnetic field to ever be anything else.
Nathan, I think you may be right about that, because if I remember the formulation by Ehlers and Ellis, I think, in that formulation, the B field does get a source, even in the linear approximation. So the source for the gravito-magnetic field, which would give you a magnetic monopole, is, I think, at least in part, the angular momentum density.
I see.
That would give rise to a gravito-magnetic monopole. So it may be apples to oranges, probably.
So, wait,
I think it very much is.
Yeah.
Gerardo, yeah. So Gerardo, is this in fully nonlinear or within the linear context that Nathan is talking about?
Right. So the formulation that Ehlers and Ellis had, and I think that's been improved by people and made cleaner and so on, but there were terms that are clearly nonlinear in the fields. But even if you wipe those out, there is a term that survives, which comes from the energy momentum tensor, which is angular momentum density. And so even in the linear approximation, you should have a source.
That looks like the sort of the equivalent of a gravito-magnetic monopole.
Yeah, right.
Huh. Okay.
And I think
Probably a visual might be the easiest way to answer this, right? It's right here in James's Quatch's paper. I figured that might be the fastest way for me to find it for you. He references those equations right there. There it is right for you, 1 through 4. So what I believe Dr. Munoz is referring to there is Jm, where J in equation 3.
Oh yeah.
And notice that you see it there? And Jm is this dual of J sub I 0 little j. And that is this funky combination of derivatives of the stress tensor. So it's very much constructed. It's very, very much constructed. If you have to define this 3-index quantity here in terms of derivatives of the stress tensor, then you need to take the dual of it, and then you find that that thing is what is related to the curl of your E and the time derivative of B. But by the way, don't be fooled by these bold notation. Those are not vectors, they are tensors.
Actually, this is really nice because it was 2 what we were thinking of, right? This rho sub m that appears in equation 2, I think.
Yes.
Yeah. So,
right? And
yes, that's rho sub m right there.
Right, it's constructed out of anti-symmetric derivatives of the energy momentum tensor. So that
exactly. That proves the point you were making, right?
Yeah. So that answers my question. That's weird because I looked at James's paper. Well, I guess a long time ago, and like I don't remember this, but that actually answers my question. Or that, yeah.
I figured the visual is much easier than talking about it in words, right? Because now we can see right in front of us. Yeah.
Well, yeah. So also then, yeah, I should go back and reread James's paper. So
now, mind you, I will mention I've studied James's paper a lot actually because I take obviously a lot of interest in this particular topic, and this particular paper, James did a fabulous job, unquestionably. I'll just mention though that these equations right here, 1 through 4. Aren't actually what you need in order to get to a final result that he obtains near the end, which is by usage of this reflection coefficient here that he has in his equation 22, which is borrowed from Ray's paper, Professor Raymond Chow's paper. So it's kind of a hybrid paper that James has here. And what I'd love to do one day, and James said he's open to this, is for us to go through and do the whole thing formally from top to bottom, derive everything, reflection coefficient, reflectivity, everything, so that we know for sure where everything came from and whether a gravitational Casimir effect, and in fact even dynamic Casimir effect, is indeed possible.
all right. So any other questions? Final comments?
I would like to make a comment, if I could. Are we still okay on time, Doug? I just have a quick comment.
Sure. Yeah, sure.
And for Nathan, I think a main point is, I just wanted to foot stomp. I think a main point that might be lost, or is worth rephrasing. It was embedded in what Nathan was saying. Is there's a fundamental underdeterminedness of the Einstein field equations. So even though it looks like 10 equations and 10 unknowns, they're actually constrained by the 4 Bianchi identity. So you only have 6 independent equations and 10 unknowns. And the other 4 equations have to come from the coordinate condition. So you can't close and solve the Einstein equations without choosing coordinates. And so that underdeterminedness really is the coordinate invariance of gravity. And so this comes into the mirages. A lot of the so-called mirages that we see, people choose a coordinate choice, and then they get the 10 Einstein equations looking Maxwellian, and then they forget the coordinate condition. So whenever we make a coordinate choice, you've actually got 14 equations to keep straight. You've got the 10 Einstein equations plus your 4 coordinate conditions. They all have to be enforced simultaneously. And if they are, all mirages evaporate, like 3 vector gravitational waves, all that funky stuff evaporates if you are scrupulous about your coordinate condition. The other point is that you can define gauge invariant, coordinate invariant fields like Nathan has, but gravity is so messy, there's no coordinate invariant forces. And so this is really a debate that Nathan and I have been carrying on. You know, you can do all this beauty in the field equations, but when you come to the force equation, you're down in the mud. You know, it's going to depend on your coordinate system, and there's no escaping it. I guess I'll pause there. That was just a main point I wanted to ram home of, you know, people get confused. At first you wouldn't think you have 14 equations simultaneously for 10 unknowns, but that's what it takes to get it right. So.
Thank you, Lance. I'd like to elaborate just a little bit on what you just said, which is that this Helmholtz decomposition theorem approach, interestingly, I think that the reason why it makes it possible to take a system that is underdetermined in the way you described is because it also, I didn't emphasize this enough really, it employs an additional constraint on how rapidly the metric perturbation falls to 0 as you go out to far distances. And that is what allows the differential equations. When you work out the nitty-gritty, you arrive at a bunch of Poisson Laplace equations and such, and the only way to uniquely solve those Laplace equations is by these boundary conditions, which then enable you to get these coordinate invariant quantities. So it's not like you won something for nothing here. The price you pay, and this formulation deserves to be scrutinized still for this, is that you're saying something about the metric perturbation across the cosmos. And we know, I think, I'm not a cosmologist by any means, I'm pretty sure we know that the metric perturbation does not necessarily go to 0 infinitely far away. So I don't even know really how valid this is. I guess you could say if it goes to 0 enough to make the approximation acceptable, then you could say it's coordinate invariant within an approximation constraint. So it's not to say that this is beautiful and perfect and it's just airtight. It still has its loose ends and assumptions in there.
And perhaps it says that the universe cannot be infinite.
I guess the thing is, because the universe is actually, it's an open universe, right? Isn't that right?
That's the general consensus, but that's not necessarily known.
Yes.
The curvature can be positive. It's within the error bound. I don't. This is not my field, but
we should also add, if we could, Nathan, real quick, the significance of the transverse coordinates, which you mentioned briefly, is that in transverse coordinates, each component of the metric corresponds to an individual degree of freedom of the gravitational field. And if you look closely, there's only 6 of them. So the magic of the transverse coordinates is it peels out those 6 true gravitational degrees of freedom, and each one of them is an independent component of the metric. And so there's also a lesson here that the gravitational field only has 6 degrees of freedom. So you've also always got these other 4 degrees of freedom that you pick to solve the problem mixing in there. And so that's why transverse is coordinates. Yeah.
That's true, and Lance and I have gone back and forth on this. He threw in a line that of course is a sticking point, because I'm sure you must know that those be fighting words, right? Because I struggle a lot with that whole issue, because the way I look at it is, once you invoked the Coulomb or transverse gauge, your previously coordinate invariant quantities now have coordinate information in them. So I just want to maybe at least piggyback I'll put it on a more friendly note. I want to piggyback off that comment and just simply say that yes, we have the beauty here of selecting out 6 degrees of freedom that all fit nicely in this one box in a sense, but we've lost the benefit, in my opinion, an important benefit, that these are no longer coordinate invariant quantities. You can make any one of them vanish with a coordinate choice. And that part troubles me about that.
And then we also have to, on the flip side, when it comes to measure, we have to, you know, we're always got that ugliness mixed in or whatever. Like the beauty the beauty that you are attracted to is now, and this is the point of our debate, is can you ever, quote, observe it, or do you always have this coordinate information mixed in? And this comes back to the equivalence principle. Yeah.
So something I did not touch on, which I could just briefly, is that we focused on the geodesic equation of motion there. And we saw that chi represents the coordinate freedom that you have that you can't get rid of because of the equivalence principle. And if you try to get rid of it, then you can make that last line go away because it's ugly. But then now these fields up here have coordinate information buried in them. My personal kind of response to that, though, is that if we were to work with the geodesic deviation equation, we don't have that issue, because what happens with the geodesic deviation equation is that the Riemann curvature tensor can be expressed completely just in terms of, let me see if I think I might have it here handy. Yes, here it is. The geodesic deviation equation can be expressed purely in terms of those gauge invariant quantities without any coordinate information encoded in there at all. So it's kind of just one of those things of what do you value? Do you really want a geodesic equation of motion? Then yes, the equivalence principle can't be avoided. If the geodesic deviation equation is acceptable, then coordinate information can be eradicated completely for the fields and the geodesic deviation equation of motion from both.
Just a comment. So if you choose a gauge and then you work with quantities which are gauge variant, but then at the end you choose an observable which is then again gauge invariant, and that sort of works, and it also often is helpful when you choose a gauge to make the mass simpler. So I think that's what happens with gravitational waves. You can choose a gauge, but then the observable at the end is not the position of a particle, but the distance between two particles, and that is again gauge invariant.
Yes, that's exactly what I trying to get across as well. That's right. So you can avoid the coordinate information problem or gauge dependence, however we want to call it, by relying on the geodesic deviation equation, and thereby avoid that problem there, right?
And only for true gravitational effects, right? So when you actually have true, quote, space-time curvature, it won't do the constant acceleration in an elevator, you know, merry-go-rounds perhaps. So I think there's some of dynamics missing from a geodesic deviation standpoint, because it only captures gravity, it doesn't capture inertia.
That's
my speculation.
That's interesting, Lance. Maybe I'll let someone else comment. I mean, my understanding is that that's true. The only thing I would say is if you hold one world line stationary, I imagine you can let the other world line move relative to that first world line and then measure whatever you want. It doesn't even have to be gravity. It could be electromagnetism or an external force. So if you hold one world line and you look at the deviation of the other with respect to it, I think you can still measure other stuff too. But again, others could probably speak about that better than I.
Well, Nathan, thanks a lot again. So if there are no more final comments and so forth, and so again, like, yeah, if you have a part 2 that you want to give in fall of 2021, we'd be happy to have you. And If I don't send you the Pacific Coast Gravity meeting stuff, like sometime this weekend, just remind me and I'll shoot it your way. Okay.
That'd be great. Will do. And thank you so much for letting me
Okay.
come and share.
All right. Thanks again, Nathan. Oh, and when we get the
Thank
video
you.
of this, we're recording this, so I'll send it to you once we're done. Okay. And oh, and can we post it? Can we post the recording of your talk?
Absolutely. Yes, for sure. Thank you.
Okay. Bye, everyone. Have a good weekend.
All right, thanks again.
All right. You too. Bye, everybody.